Hello students, this is Vishal Vishwakarma and today we are studying about the, what is the origin of quantum mechanics and how it is uh, came into existence when came into existence to understand the world and how it behaves. We will understand that and what kind of theories which are dependent on it, so that we have a fruitful analysis of it, quantum mechanics, such that we can able to understand that why it came. So basically quantum mechanics is a subject to understand the particles, that how it behaves, how it moves, how it goes from the the mechanics of that particles, how it goes from one place to another place and act like that. To understand these all topics, these all to analysis of all these mechanics of any particle, we we invent the subject of quantum mechanics. So if you see, it is largely depends on the comes from classical concept. When the classical theory fails, basically when the classical theory fails, at that time, the quantum mechanics came into existence, uh, because the if I remember that the the starting of this quantum mechanics started from the topic of I want to say that the topic of how uh, why the topic called as ultraviolet catastrophe. So the ultraviolet catastrophe when came into existence, that this kind of this kind of invention has to happen. What is ultraviolet catastrophe? If you understand what is ultraviolet catastrophe, you saw the Jeans law. So classically Jeans law say that the intensity of any light, the intensity of any light is is goes from intensity of light is directly proportional to the frequency, is the square of frequency. So basically the square of frequency, if you see that square of frequency term, so it is not very much alien to us, that square of frequency can take a great result, but not in visible light of electromagnetic spectrum, not in the infrared region, but in ultraviolet region. If you see, the ultraviolet regions of frequency is it started from 10 to the power 6 14 to 10 to the power 16, right? So 10, after 20 to 10 to the power 14 to 10 to the power 16, this kind of huge frequency, when you square it, you got the 10 to the power 32, right? So if that means the intensity goes in ultraviolet regions to 10 to the power 32. This much kind of energy we can feel as in ultraviolet region, if we capture the ultraviolet region. But this is doesn't happen. You can see easily that if we go from outside in a park or any place, the open space has came with full with ultraviolet region. So we cannot feel that kind of heat, that kind of heat which is given by the classical laws of 10 to the power 10 to the power 32. We don't feel that kind of heat, right? We only feel a very low heat. So this is not happen practically. So practically there's something else happen, which is seen as which is seen to us, that practically which is seen to us in a visible region. A very low light came to us, right? So to this is not a practical, but practical things are different. Practical things, we feel practical things, that this kind of things that's not happening. So here the concept came that at that region of at that region, we feel so much heat in that, according to the classical laws of genes, we feel so much heat, but this doesn't happen. So what is the right thing? So in this picture whole, then Planck's came and the graph of the black body radiation he plotted, as you see in your presentation, or this picture, there you see a graph. The graph, which is the formula is underwritten in that graph. So you see that graph. So the Planck's came and the plotting of this graph. With the help of plotting of this graph, he invented a formula, derived a formula, which is called Planck's radiation law, right? So at that Planck's radiation law, he did that, right. At Planck's radiation law, he came with a concept of H. The first time the concept of H was came in the Planck's radiation law. It is the invention of H. So this H, the Planck's constant, 6.6 to 6 10 to the power minus 34, this much value. With this value, we we he came with the Planck's constant 6.6 into 10 to the power minus 34 joules per second. That kind of invention of the formulation of H came into existence with the Planck's radiation law. So if you see the Planck's radiation law, it is the origin of quantum mechanics. So I am just discussing the law. It came from Planck's radiation law came from ultraviolet catastrophe, which is the topic which I am saying to you, right? So so thank you very much. Hello students, this is Vishal Vishwakam, and of Professor Assistant Lecturer of Physics from TIA Technograd Group of Institution. And today we are learning about the topic of quantum mechanics and the origin of quantum mechanics. Previously we discussed that in previous slide we discussed about the ultraviolet catastrophe, and right. But now we are discussing about the second slide, which shows you that the duality in the nature of particles, right. The dual behavior of the particles, basically, to understand it as a as a as a fruitful topic for you, I hope. And let's start it. So after the problem solved after ultraviolet catastrophe, we got that, and obviously the Einstein's helped so much about that, uh, about to understand the light, how it behaves in its nature, in a very deep to a particle way, and obviously in a wavy way, a way of waves. So it is really right that it is really right that after ultraviolet catastrophe, we have two new different kind of phenomena, which is we have two different kind of experiment happens in different places of Earth, or different places of this world, in which the particles have been shot out or shoot through two slits, and we find how it behaves like, right. So how it behaves. So we shoot particles from two slits, and this is called electron diffraction experiment. So as we understand that the quanta is emerged from the from quanta is emerged from, right, from understanding of the light, right. But when we go to electrons shoot through two slits, it same behaves like a wavy way, right. It's wavy way means the wave nature. It shows the wave nature at the screen when we got diffraction pattern, right? We got diffraction pattern of electron. So electron or any solid particles we threw are two slits, right? So this kind of behavior was not understood. It's out of understanding that how a solid object can be explained or defined uh, uh, a wavy nature, right? So this is the wave particle duality. So particles also show the wavy nature. That's and in this picture, in this whole picture, then Planck's came. Oh, sorry, the de Broglie came, and they said that if they derived a formula, they present a invented a formula and presented in its paper that matter wave, right? In this matter wave they say that lambda is equals to h by p, right? So h by p, basically this h by p part, if you see, the lambda is the property of wave, right? The wavelength, we all know that. And uh, the p is the momentum, right? It is the momentum, and it is a property of particle, the solid object, right? So and h is the Planck's constant. Okay, so he derived a relation which relate the wavelength lambda with the particle's momentum p, and it gives the relation between these two things. So you got the idea of it, that at lambda you got a wavy nature, at p you got a particle nature, and the connection of these two with the help of the Planck's constant h. So basically it is a very a new concept at that time. If I remember it, it's a time of 19th century. So the paper was very astonishing, and yeah, they derived and they explained in it that the particles will be behave in two ways, the wave and the particle wave, and they derived the formula lambda, as I tell you, h by p. So in this regard, if you see this the top the your presentation in which like the wave duality is a core quantum concept, says all matter and energy like electrons, photons behave both waves and particles depending on how you observe them. This means light, once thought only a wave, acts like a particle. Photons, particles like electrons, acts like a wave, revealing the dual nature through experiments like photoelectric effect and double slit experiment wave, right? So if you see this whole concept of the name, uh, the picture you have seen in this presentation, that the two waves are adding with the same phase, and it gets, if the waves have the same phase, you get the bouncy, the more uh, intense wave, and the addition of that, if it is a phase, if they are out of phase, you got the zero, the lowest low intensity, right? And if you see the refractions happening, this diagram is in front of you, which saying you the diffraction pattern, and the waves goes through two slits, and the wave, you can see the wavelets forms from the two slits, and the diffraction pattern happens in diffraction pattern formed in the screen, right? So basically this as you see that this topic is so this is the nature of wave, and the electron thrown through it, through the two slits, you got the same behavior which shown in the case of only waves, right? So that's why we say that the particles behave like the the particles behaves as in this world like a wave, uh, and the wave and the particles, the and the light, which is the seen as wave, it behave like a particle, which we seen in a photoelectric effect, right? So these two are effects of the quantum mechanics, and the quantum mechanics started from these young double slit experiments, and the double slit interference experiments, and the photoelectric effect, and before that the ultraviolet catastrophe, and before that the 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 Planck's radiation law, and all these are the starting stepping stones of the 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 origin of quantum mechanics, right? So I hope you understand that duality, and in this regard. Okay, thank you so much.